Hi everyone, I am Sona Hassani and I'm going to talk about our paper on faster algorithms for generating explanations for multiple predictions. This work is done in collaboration with Saravanan Tiramuruganathan from QCRI, Nick Kodas from University of Toronto, and Gautam Das from the University of Texas at Arlington. We all know how machine learning algorithms work. You train a model on a training data and then use it to make prediction on an unseen data. This machine learning model looks like a black box to many domain experts, such as a physician or a manager. They don't know how or if they can trust the behavior and output of this model. Therefore, a line of research called explainable AI attempts to generate human understandable explanations for behavior and output of a machine learning model. For example, if you use a machine learning model to predict price of a house, then explanation about this prediction could be, this house costs this much because it is located in a nice neighborhood, it is fairly new, and it's designed by a famous designer. As you can see, model explanation is a great way for debugging an ML model and for understanding whether or not it's doing the right thing. There are many scenarios that you may want to generate explanations for more than one prediction, and then you need to repeat this explanation process over and over again. The problem with existing explanation methods is that they are highly optimized for generating explanations for one single data point. We define our problem as generating explanations for multiple predictions. Given a batch of tuples, a classifier, and an explainer, we want to efficiently generate explanations for each of tuples such that the cumulative cost of computing explanations is minimized. Why do we need to speed up explanations? Because generating explanations takes time. It is not done in real time. If an SVM model makes a prediction in 50 milliseconds, then generating explanations for that prediction using existing explanation methods can take about 10 seconds. A popular and widely used category of local explanations is model-agnostic local explanations, which these methods are mainly perturbation-based. So these explainers, given input data point with the prediction and a black box classifier and some information about the training data, they generate samples using perturbation methods based on the information they have about the training data. Then they invoke the black box classifier on those samples to generate labels for them. Then they do some post-processing on the label samples, and finally, they explain the behavior of the classifier. We propose a framework inspired by multi-query optimization technique in database field to efficiently generate individual explanations for every point in a batch, which is optimized for the batch. In our framework, the input is a batch of data points with their prediction, and then through the explanation process, we do some pre-processing and utilize caching the partial results and materializing some pre-computations and other database techniques to generate explanations more efficiently. And then we output all of the explanations of the given input batch together. We also looked into the streaming scenario. In the streaming scenario, you do not have access to all of the predictions in advance. The data points and their predictions come one by one, and you want to generate explanations for them as they come. In this scenario, also, we can cache some partial results and utilize that to generate explanations more efficiently. So there are some ideas for optimization. Through profiling the current explanation methods, we realized that one of the most time-consuming steps in the sampling-based explanation methods is calling the black box classifier on the generated samples to label them. Through our experiments, we saw that about 88% of line of the execution time of Lime, and 92% of execution time for Anchor are spent on invoking the black box classifier. I will explain these algorithms later. Also, we wanted to avoid repeating the redundant computations for common units. And one way of doing this is using frequent item sets. And finally, in some of the algorithms, there are some invariant items. For example, there is precision or coverage, which regardless of what sample you are using, their value will not change. And through our framework, we wanted to avoid recalculating the invariant parameters in the explanation process. So the general algorithm is as follows. Given an input batch of predictions, we take a uniform sample from this batch and then find frequent item sets over it and generate a fixed set of perturbations for each item in the frequent item set, then invoke the black box classifier on these perturbations to label them and generate the samples and their labels in the storage. Now, for each tuple in the given batch, we reuse the relevant samples and labels from this storage and explain that tuple based on the internal algorithm of the explainer and modify this storage if required. And finally, we output all of the generated explanations. Now look at each algorithm more closely. Lime is one of the most popular local explanation methods. The explanation format in Lime is a subset of feature values along with their contribution towards the predicted label. This contribution can be positive or negative. Lime first samples around the given data point using perturbation and then calls the black box classifier to label those samples. Then it measures the distance between the generated samples and the original data point. It runs some feature selection, and finally it trains a surrogate function on these label samples to use for generating explanations for the original data. To use our framework for Lime in a batch scenario, given a batch, we take a uniform sample of this batch, then find frequent item sets over it, generate a fixed set of perturbations for each item in the frequent item set, then invoke the black box classifier on these perturbations to label them, and store these samples and their labels in storage. Now, for each item in the batch, we retrieve the reusable samples and labels from the storage, and if there are more samples required, we only generate the required samples and call the black box classifier to label them, and then compute proximity between these labeled samples and the original data point, train the surrogate function, and generate explanations. Anchor is another popular local explanation method, which is sampling based. So in Anchor, explanation format is a rule, which is a subset of predicates that predicts the output of the classifier with some precision. Anchor iteratively generates candidate rules, and in each iteration, it estimates the precision for the generated candidate rule. Estimating the precision is done through sampling based on the candidate rule and calling the black box classifier on the generated samples to label them. And in each iteration, the partial rule or candidate rule with highest estimated precision is selected, and this loop continues until the current candidate rule meets a threshold, a precision threshold for being an anchor. And the steps that I have highlighted are the steps that are the most time-consuming steps in this process and where we can utilize to do some optimization. Now, to apply our framework to anchor algorithm in a batch scenario. Given a batch, we generate a uniform sample over this batch and then compute frequent item sets, generate candidate rules using these frequent item sets, using sampling and then calling the black box classifier on them and estimating their precision. Now, for each item in the batch, we see that if any of the, in each iteration, if any of the candidate rules for this item already exist in our candidate rule storage, then we can use, basically retrieve their precision and check whether or not that meets the threshold criteria or not. If yes, we can use that one as an anchor. And if no, we can still bootstrap the precision from our storage and use it for continuing on expanding the partial rule and calculating the precision of the next steps. And kernel SHAP is another well-known local explanation methods. Kernel SHAP is based on Shapley values, which is Shapley values are used in cooperative gaming for calculating the distribution of a prize among different players of a game. And kernel SHAP generates multiple random feature subsets for the given data point, then estimates their weight through the SHAP kernel. Then it converts each feature subset to random perturbations through sampling from the training data distribution, and then it applies black box classifier on the random data perturbations, and then it trains a weighted linear regression model and then computes Shapley values for each feature. Again, the steps that I've highlighted are the steps that we can use to optimize for a batch scenario. Now, for applying Shahin's framework to kernel SHAP in a batch scenario, given a batch, we generate a uniform sample, then we compute frequent item sets, we generate a fixed set of perturbations for each item in the frequent item sets and invoke the classifier on these perturbations to label them and store these samples and their labels in a storage. Now, for each item in the batch, if that item contains any of those frequent item sets that are already generated and stored in the storage, we can retrieve the samples and their labels that are generated for those frequent item sets. And then if more subsets are required, we just generate samples for the remaining of the subsets and call the black box classifier to label them, and then proceed with the remaining steps of kernel SHAP algorithm, such as computing weights of each sample using kernel SHAP and training the interpretable model and generating the explanations. We also looked at the streaming scenario. In the streaming scenario, the tuples and their prediction come one by one, and we want to explain them as they come. In this case, we assume we had two additional storages, one for storing the generated samples and labels, and one for storing the explained tuples. Now, for each tuple in the stream, we generate required samples for this tuple, and then invoke the black box classifier on these samples and store the samples and their labels in the sample storage and the tuple in the tuple storage. And use the explainer to explain this. Now, if the budget for the sample storage is met, we discard the additional samples based on the least recently used strategy. And if the budget for the tuple storage is met, we calculate frequent item sets over this storage to utilize and use later in a similar fashion like our batch scenario. Um, to look at some experiments that we did for Shahin's framework, this page shows the the time spent by um, um, time spent for generating explanations for one single data point using the sequential baseline and Shahin in the batch scenario and Shahin in the streaming scenario for 3 different explanation algorithms, Lime, Anchor, and SHAP, and 5 different data sets. And as you can see, in the columns on the right, the numbers are shown in seconds. The first number shows the time taken for the baseline. The second number shows the time for the batch implementation, and the third number shows the time for the streaming scenario. And as I can see, the batch scenario outperforms the baseline by an order of magnitude, and streaming scenario, even though is not as good as batch scenario because we do not have access to all of the data points in advance, it is still shows significant improvement compared to the baseline. Here in this slide, we see the speed up achieved by Shahin and baseline algorithms. And as you can see, Shahin, which is the blue line, outperforms all of the baseline algorithms, especially when there are the batch size grows. For example, for a batch size of 1K, you can see that it significantly outperforms the baseline algorithms. We observed here in this slide, we can again see the speed up ratio for Shahin for 3 different explanation algorithms and 5 different data sets, and how the speed up ratio changes based on the change in the batch size. And we observed a similar trend in the streaming scenario. And as you can see, as the size of the stream grows, the speed up ratio improves significantly. We also looked at the overhead and other parameters in our framework. So there's some time taken for housekeeping, for example, finding frequent item sets or retrieving the reusable samples. And as you can see, this overhead, which is the percentage of time used for housekeeping compared to the total execution time, it drops as the batch size grows. For example, for a batch of size 1K, the overhead is about 3% of the execution time. We also looked at the impact of the number of perturbations we generate and impact of cache size. For more details, please refer to our paper, and please contact us if you have any questions. Thank you very much.